Okay, here we go, my BC kids. We are into section 10.4 on the integral test for convergence. Remember, we're in a unit of sequences and series and deciding if they converge or diverge. So this is just another test for you to be able to test for convergence. And it says, if f is positive, continuous, and decreasing for your x is greater than or equal to k, and a sub n is equal to the function f of x, then, here's what it says, the sum as n equals k to infinity of your a sub n, we've seen those before, and the integral from k to infinity of f of x dx with respect to x, they either both converge or both diverge by the integral test. So whatever one does, the other does. It's either going to be both of them converging or both of them diverging. But the deal is it has to be a positive a sub n, the function has to be positive, continuous, and decreasing. So every time you want to use the integral test, you need to test those three things. I feel like I'm blurry, so I'm going to... There we go. That looks a little better. Okay, so here's some theory behind it. Now remember, it has to be positive. These are the things, positive. It has to be continuous and decreasing. Those are your big things. So I'm looking at this function. It comes down here, it's positive, right? Because all your y values are positive. It's continuous, no blips or blaps in it, and it's decreasing. All of your values are getting smaller. So if I'm looking at this point right here, these are like the left and right Riemann sums. This point over here is a sub 1. Well, that is the same thing as f of 1. This guy here would be a sub 2. This guy here would be a sub 3. And you know it continues on. How many rectangles could I put in there? I could put 1,000,000 rectangles, an infinite number. Sorry, not that guy. This guy down here, he's a sub n. And this guy here would be your n plus 1. But we don't use them because see how we're using left-hand sides? All right, so that's what I would look like. And here's what the mathematical jargon would say about this. It would say you've got a summation where n equals 1 to infinity of a sub n. And you can see that those a sub n's are greater than or equal to the integral of your function, going from 1 to n plus 1. Notice we didn't include that, but n plus 1 is where it is for my function. And what that's saying is that if I look at this, this is an overestimate. I'm going to change my color. Overestimate. When I take that integral, it's going to give me a value that's bigger than the actual value for the function. It's an overestimate. You can see that you've got spaces of the rectangles that are outside of the function that you don't need. Like this would be an over part, this would be an over part, and so on down the line. So it's an overestimate. And so if I think of that as n approaches infinity, so here's a new jargon, as n approaches infinity, let me move this so you can see me better. There we go. I would have this statement to say, kind of like, now I'm bringing in the sandwich theorem. Ooh, gosh, remember these things from back in the day. 1 to infinity of f of x dx. I take that integral is less than or equal to the sum as n equals 1 to infinity of a sub n is less than or equal to the integral from 1 to infinity of f of x dx plus some constant. Remember integrals with your constants. So you can see it's kind of sandwiched in there, that this a sub n sum is sandwiched between the integral of your function plus your constant and the function itself. So that's what the first drawing is trying to say to you. Second drawing, this one on the other side, this is like a right Riemann sum. All right, well, a sub 1's over here, so this would be a sub 2. That makes this a sub 3, which, if I keep going, this is now a sub n, and this one now I'm including, and that's a sub n plus 1. Now, how many rectangles could I have? I could have any number, an infinite number of rectangles. So I'm looking at this, and I'm comparing the sum to the integral. My sum this time, n equals, now what does it start at? It starts at 2. And what does it go to? It goes to n plus 1 of a sub n. And this time all of my rectangles are below the integral, or below the curve. So below, it's going to be less than or equal to, instead of greater than like the other one was, the integral going from, if I look at this, it's going to be 2 to n plus 1. Actually, that's not true. It's going to be from 1. Even though I didn't include, just like I didn't include the n plus 1 over here, I'm not including the 1, but it still has to be part of this integral from 1 to n plus 1 of f of x dx. And you can see that this is an example of an underestimate for this. Underestimate. Because my rectangles are now below and there's spaces that are not included in this. So you can see that. All right, so another mathematical jargon, and this one's kind of interesting because what we're going to do is add a sub 1 to both sides. The one that I didn't include, a sub 1, well, I wanted to say add a sub 1. There we go. Add a sub 1 to both sides. And it's going to create this mathematical statement that the sum n equals 1 to n plus 1 of a sub n is equal to the integral going from, if I add 1 to both sides, I'm going to be going from 1 to n plus 1 instead of just the a sub 2. It's going to be adding one more to both sides. So I have a 1 to n plus 1 of my function f of x dx. And then I have to add on that a sub 1 term. So if I look at that, this is what this jargon is actually talking about. Does this come up a lot? No, I believe there's one practice problem that might refer back to it. So if you're hung up in there, don't get too hung up in there. It's not really that big a deal. And it's not going to come into the actual application of the question. Here's the big stuff to remember. Big stuff to remember is that if you want to use the integral test, you have to make sure that that integral is positive, continuous, and decreasing. Otherwise, the integral test will not work. Okay, so let's try a couple problems, see how you make out. Number 1, see this one is 1 over n times the ln of n, all your denominator there. And by the way, there's going to be a whole lot, oh, sorry, Maddie, but a whole lot of u sub and that type of thing. There's even going to be one that we do that's integration by parts. So that's going to be some interesting stuff too. All right, determine the convergence or divergence of these series. And so I have 1 over n ln of n. And if I think about the tests that I've learned so far, there's none that look like this one at all. Like, it's not a geometric series. It's not anything that we've seen up to this point. So let's test it. Let's see. Is it positive? Is it continuous? Positive, continuous, and is it decreasing? If I think of numbers in here, my numbers start at 2. If I put in a 2 to infinity, 2 ln of 2, 3 ln of 3, infinity ln of infinity, what happens with this function? Is it ever going to hit 0? And the answer is no. It's not going to ever hit a 0, right? You're always going to have positive values coming out. So this one's checked. Got that. Is it continuous? Well, it would be discontinuous at 0 because you'd have a 0 denominator. But 0 is not part of my domain, so yeah, it's continuous from 2 to infinity. And is it decreasing? Are these fractions getting smaller? So in other words, is the denominator getting bigger? If the denominator is getting bigger each time, then that means that this is getting smaller. So 2ln of 2, 3ln of 3, 4ln of 4, they're all going to be decreasing values when I put that in there. So there you go. We've got all the parts ready to go for this thing. So here's what I've got to do. I'm going to take the limit. This one's now a limit. I wonder if they should have said that up in the box, but they didn't. But anyway, the limit, I'll show you how it works, as b approaches infinity for the integral from, it started at 2, so 2 to b, 2 to infinity, of 1 over n, ln of n, dn. So that's how you're going to find these. You're going to set up this limit for the integral. And if I look at this, I'm thinking of how I can integrate this. So I'm going back to my BC roots, and I'm thinking, well, geez, it kind of looks like a u sub. So if I u sub and let u equal the ln of n, what will du look like? And you say 1 over n dn, and I say, check that out. I have an ln, that would be u to the negative 1. I have a 1 over n dn. I can substitute that in, and so I can see that my next job on this is going to be the limit as b approaches infinity for the integral of 1 over, going from 2 to b, by the way, of 1 over u to the negative 1, du. All right, so here's what I've got then. 1 over u, if I integrate that, that's the ln of u. So I'm going to have the limit as b approaches infinity of, now if I'm taking the integral of that, it's going to be the ln of u. The ln, maybe I'll do this the long way. The ln of u going between 2 and b, infinity. But what is u? U is the ln of n. So I'm going to substitute that back in, so I'm not going to change the bounds. So here's where I'm at next. The limit as b approaches infinity of the ln of u going from 2 to b, infinity. Now I'm ready to substitute it in. So if I have the ln of b minus the ln of 2, f of b minus f of a, this is what it looks like now. Well, what is b? b is infinity. So this piece here would be like the ln of infinity. Think of the ln graph. What's it doing as it goes to infinity? It's going to infinity. So this would be infinity minus the ln of 2. And do you really care if I take infinity and subtract some smidgen from it, then I still get infinity. Now if the answer is infinity, then that means that this thing diverges. Because the integral diverged, then the sum is going to also diverge. And that's what it comes into play with this one. So this, your integral diverged, which means your sum is going to diverge too. All right, try another. To the right, to the right. This one is actually a p-series, would be the easiest way to do this, but you don't know the p-series yet. That's in the next section. So since we know only a little bit, let's check it out with the integral test. So again, I want to check, is it positive? Is it continuous? And is it decreasing? And so if I'm looking at this, 1 over n squared, it is always positive. It's never going to hit 0 or be negative because you've got a squared value there. Is it continuous? It's like the 1 over x graph. Can't touch this. Kind of similar to that, except both parts are on the positive side. Is it continuous? Yeah. Is it decreasing? Is my denominator getting bigger and my numerator staying small? And you say, yep. So there you go. It's got all the criteria. So let's check it out. I'm going to take the limit as b approaches infinity for the integral of going from 1 to infinity, or 1 to b, I should say, since I'm using the b. Why do they do that, by the way? Do you remember that? This is like an improper integral. So since it's an improper integral, you have to put it into improper terms, if you remember that from back with improper integrals. But anyway, I have 1 over n squared, or n to the negative 2, dn. And I can just integrate that. I don't need any by parts or u subs or any of those things to make this one work. So I'm just going to directly do that integral. The limit as b approaches infinity, and I am taking the integral of n to the negative 2, makes it be n to the negative 1 times a negative 1. So it's negative 1 over n to the negative 1 times a negative 1, going from 1 to b. All right, let's put it in there, direct substitution. It's going to be negative 1 over b minus negative 1 over 1. Well, b is infinity. 1 over infinity, negative 1 over infinity, is 0. And then I have negative negative 1, so plus 1, and I get a 1. And since I got a 1 out of this thing, a distinct number, I've got that this thing converges. So this one converges, where this one was an infinity answer, and that one went to, that one would diverge. All right, that's the 2 examples that go with this section. We're going to pick a few of the practice problems to look at. First one I want to do, funny enough, is number 1. Number 1. If the integral test applies, use it to determine whether the series converges or diverges. All right, so this one is n over e to the n, going from 1 to infinity. So I want to know whether I can use, first of all, the integral test. So it has to be positive, continuous, and it has to be decreasing. So let's check it out. Let's check out the first few terms. If n is 1, I would have 1 over e to the first. If n is 2, remember this is a sum, if n is 2, I would have 2 over e squared. If n is 3, 3 over e cubed, and so on down the line. So I'm just going to take a few points to see what happens with them. Well, e is like 2.718, so 1 over 2.718, 2 over 2.718 squared would be like a 7 point something, and so on down the line. If I look at this, I can see that they are all positive. I can see that they're continuous. There aren't any bumps or hitches in it. And I can see that each fraction is getting smaller, so that is decreasing. So it fits the criteria. All you're doing is taking just the first few terms to test them out and think about what that would look like. All right, let me set it up for my integral test. The limit as b approaches infinity for the integral going from 1 to infinity, 1 to b. And I am, let me write it this way, n times e to the negative n dn. Now we haven't seen one like this for a while. If I have 2 pieces being multiplied together and I want to integrate them, then here's the story with this guy. This is no longer a u sub. That's not going to get me anywhere with this one, because you would probably pick e to the negative n, and then it just gets into a whole nightmare. So that's not going to work with that, but you can use by parts. Holy moly, we haven't seen that for a while. But by parts, here's what by parts says. You take u times v minus the integral of v du. That's what by parts says. I believe we might have used an f of x times g of x minus the integral of g of x and f prime of x. Something like that we might have used. But this is the standard one from back in the day. U times v minus the integral of v du. So then you have to have u is one part, u is my n, and then the second part I have is my dv. This is u times dv. That means my dv is e to the negative n dn. But then I need the other parts of this. So the other parts of this are going to be du, well, the derivative of this, du, is going to be 1 dn. This is the derivative. If I go backwards and figure out what v is, this is the derivative. I want to go backwards and figure out this. This would be negative e to the negative n. It would be e to the negative n times negative 1. And so if I'm looking at that, turn off my volume here. Now I have my 4 pieces. I can do by parts. So here's how it's going to look. It's going to be the limit as b approaches infinity for, all right, u times v. U is n. V is a negative e to the negative n, u times v, minus the integral of v, negative e to the negative n, du dn. Now that's going from 1 to b. But I've got to continue on. I've got to actually take the integral of this part right here to clean this up. So then I can have a b minus f of a. So I've got the limit as b approaches infinity of negative n e to the negative n plus, this gets a little hairy, it's going to be plus because of these two, but the integral of e to the negative n is a negative e to the negative n, going from 1 to b. Now let's plug this in. It's going to be substitution. So I'm going to take the limit, still limiting, I haven't put in my infinity yet. N becomes b. So it's going to be a negative b over e to the b plus, actually minus, 1 over e to the b. 1 over e to the b. This is e to the negative b, so it's going to be an e to the b on the bottom. And then it's going to be minus, put a 1 in, negative 1 e to the negative 1, 1 over e, minus negative 1 over e to the first again. Whew. Well, if I put infinities in here, these are infinities in the denominator, that means that they're going to become, I'm going to go into box 3 just so I have some space. I'm going to have e to the infinity in each of these denominators. They become 0. And then I have, let's see what I have here. I have a negative 1, actually negative 1. So that makes this plus, this is going to be 1 over e, plus a 1 over e. And if I have 1 over e plus 1 over e, they're same denominators, I can add them together. This is a whole lot of nothing. Then I have 2 over e, and that's going to be my answer. So that means if it's 2 over e, it's going to be therefore converging. Crazy. All right, one more. Maybe 2. But number 4 is next on my list, and I chose it because I know how much you love trig functions. So let's trig function this one up. Again, I need to check, is it positive, is it continuous, and is it decreasing? Well, let's check. I am going 1 over n squared times the sine of pi over n. We already talked about 1 over n squared, didn't we, in that second example? We know that that part's positive, continuous, and decreasing. Is the sine of pi over n also going to be positive, continuous, and decreasing? And so I'm going to think about that. If I put in a 1, sine of pi, sine of pi is negative 1, 0. The sine of 0, this ends up to, well, you know what, maybe let's try plugging in some points. Let's check it out. If I put in, I can't start at 0, so it's got to be a 1. If I put in a 1, I end up with a positive value for this. And we can graph it. Maybe we want to graph it. Because that gets a little hairy. What's it doing at the sine of pi? That's a sine of pi. I need to, you can't see me. You can if I put my, there we go. All right, one thing I need to do is change my mode. I know I was doing something for pre-calc where it was a degree. Okay, so now I'm good. Y equals, clear, 1 over n squared, I'm going to use parentheses, 1 divided by x squared times the sine of pi over x. Cool. Graph it. Okay. Now I know that that looks like a whole funky thing there, but really I'm only concerned about values of n equals 1. So let me go to my table. It starts 1 is 0, and then the next one, I'm looking at my table here, if I have n is 2 is 0.25, n is 3.09, n is 4.04. Are they continuously getting smaller? They're all positive, right? Starting from 1 is 0, and then it goes to 0.25, so it's a quarter. And then it goes to 0.09. So they're all positive values after 1, because that's, see how my bound here goes to 1 to infinity? So I'm looking at it from 1 on, and I see that each one's continuous. I can see that from the picture of the graph, and they're all getting smaller. So it does fit all the criteria for what you're looking for. All right, here we go. I'm going to set it up so that I can take the integral. The limit as n approaches infinity for, as b approaches infinity, b. The integral from 1 to b of 1 over n squared times the sine of pi over n, and I am with respect to n. Now this one's a little trickier, which is why I chose it. This one's going to actually be a u sub. And what are you u subbing? You're u-ing this weird angle of pi over n. If I du that, or I guess I could say pi n to the negative 1, that might make it a little bit easier to du. And if I du that, then it's going to be negative pi to the n to the negative 2, 1 less power, dn. And if I look at what I have a 1 over n squared. Well, that's this piece. What I don't have is this pi being involved in that. So I need to move that to the other side. If I do that, that's going to be dividing by negative pi. So now I've got negative 1 over pi du on the left, and on the right I have 1 over n squared dn. All right, let's set up our substitution on this. So if I substitute into this limit, one to b, I always want to put that infinity up there, 1 to b, which is infinity, I will have a substitution of sine of u, and this is negative 1 over pi du. So negative 1 over pi, this one is the sine of u du. Now that's what I need to then, this is a constant, so then I need to take the integral of that. So if I take the integral of that, it is going to be the limit as b approaches infinity for the integral of sine is negative cosine. That negative cosine comes out and bops out this negative sign that's there. So what I have is just 1 over pi. Cosine of u, going from 1 to b. Or I could say the limit as b approaches infinity for 1 over pi cosine of infinity b, and then I have I guess I don't, yeah, I still need that. So 1 over pi, I'm looking at my things here, 1 over pi cosine of 1, right? F of b minus f of a. So if I look at that and think about where I'm going next with this thing, it would be like this part here saying 1 over pi cosine of, my u was, maybe I should leave these as u's for now. U's. This u, what is u? U is pi over n. Or pi over, in our case, b, right? Pi over n. Pi over b. That would be this first piece. Second piece is 1 over pi cosine of pi over 1. All right. Well, pi over b, think b is infinity. If b is infinity, then pi over infinity is 0. What's the cosine of 0? That's what this is asking you for. So I have 1 over pi, but it's times the cosine of 0. And that's going to be subtracting away 1 over pi times the cosine of pi. And I've gone off the screen. All right, so cosine of 0, if I go around to 0, the x value is 1. So if this is 1, then I have my first piece here being 1 over pi times 1, 1 over pi. Second piece over here, the cosine of pi, well, that's the coordinate -1, 0, and the cosine's the x value. So now I have 1 over pi times a -1, but it's going to be negative, so it's really plus 1 over pi. Gives me an answer of 2 over pi, and therefore I know it converges. Are we loving these yet? These get pretty long. The lovely integral test. All right, let me see if there's any others on my list. Number 11 was last on my list. Let me give you some clues for a couple of them as we come along here. On this page, for number 8, I would highly recommend that you graph it for 8 and 9. For 8 and 9, I would use my calculator and graph these guys. That's helpful with them. You're explaining why the integral test doesn't apply and show that that it meets the criteria for the integral test. So use the graphs to help you with that. That would be my hints for those two. I said I wanted to look at number 11. This will be the last one, I promise. Which of the following can be used to determine the convergence or divergence of this series? I'm looking at the series from 1 to infinity of n plus 3 over n plus 4. So properties of the geometric series. So if I'm looking at this, is this set up as a geometric series? Remember, geometric series were a r to the n. They kind of you have to have a ratio of some sort, a common ratio. And this one doesn't have that. There's nothing being raised to the nth power, so there's no r value for this guy. So this guy doesn't apply. How about the nth term test? Well, the nth term test says take the limit of that thing. It says take the limit as n approaches infinity for n plus 3 over n plus 4. This is the nth term test. Maybe I'll put an arrow. Boop. Well, what's the limit of that? That's like a horizontal asymptote, right? So n over n means that that is 1. And if I look at this, which of the following can be used to determine the convergence, that one would work because remember it's just a can equal 0. So it came out to be 1 and therefore we're good with that one. For the integral test, so the integral test, does the integral test apply to this? Let's try the first few terms and see if it's positive, decreasing, and continuous. So if I have n plus 3 and I start at 1, 1 plus 3 is 4, 1 plus 4 is 5. Cool. If I do the next term, it's going to be 2. Now it's 5 over 6. And then it's I'm sorry, I'm looking ahead. 5, then I'm 3, so 6 over 7. What's happening with those fractions? Are they getting smaller or bigger? If I do even the next one, if I go to 4, then I'm at 7 over 8. Are they getting smaller? Are they decreasing? I don't think so. If you're not sure, let's check it out. Back to my calc here. If I go to dividing these, 4 over 5 we know is 0.8. Right? If I do 5 divided by 6, oh, 0.83. That's not good. Not good for the integral test anyway. If I do 6 divided by 7, now I've got 0.857. So what's happening with these guys? They're getting bigger. They're not decreasing. So this guy's a no. It's not decreasing. So which one could be used for finding convergence or divergence? The only one that fits is number 2. So just kind of a good reminder of some of the other tests we've learned so far. All right, have at it. Your task is to complete numbers 1 through 13, and I will see you in class. Shoot me an email if you've got questions. See ya.